Hi everyone, very glad to be here, my first JVM Language Summit. I've been watching virtually for a number of years, and so it's good to be here and enjoy it in person, and also be talking about using some of the product of all that work that I've been watching for the last couple of years in our work on the Scala compiler. I'm from Lightbend, so is Adrian over there. We're on the compiler team. So today we'll be talking a little bit about the upcoming release of Scala 2.12, what the themes of that release are, what the new features are for, and improvements are for our users and for ourselves as implementers. We're then going to drill into a couple aspects of that, how the encoding of Scala traits has improved because of the use of Java 8 features, how we've been able to use invoke dynamic in our implementation, and expose that also to our users to experiment with, and finally how our Lambda encoding looks now. I'm happy to take any questions as we go as well, so if something's needs explaining on the Scala side of things or anything, please feel free to shout out. So the main purpose of Scala 2.12 is to upgrade our platform, which is to drop support for Java 6 and Java 7 and require Java 8. The reason that we've done it in this way rather than just offering targets for 6 and a target for 8 is sort of tied up with the binary compatibility story of Scala a little bit. Our major releases are not binary compatible with previous major releases, so the open source ecosystem kind of regenerates itself each Scala major release. These things happen about every 2 years. Because of that, we didn't want to introduce an extra fragmentation point where the open source authors had to, produce versions for 6 and for 8. So that one fragmentation point of the Scala major version we thought was enough. And based on the adoption rate that we've seen and that you guys have seen for Java 8, we think that the time is right for this upgrade. After doing so, we're able to exploit the new features in the JVM, and we can improve interop in ways that people will expect now that they're used to Java 8 itself and the APIs that are produced in the Java standard library and by other authors who are targeting Java 8. Aside from that platform upgrade, we've also been doing some internal renovations, cleaning up some technical debt. So we've brought online a new code generator in the back end, which has a new implementation of our ahead of time optimizer. Non-goals have been sweeping language changes and features, and also sweeping library changes. It's been our goal to make the transition from Scala 2.11 to 2.12 as seamless as possible, given that some people may need to still be supporting Scala 2.11 for some time when they're restricted to older Java versions for one reason or another. So let's dive into traits. So a quick description of what traits are in Scala. So just like in Java, a Scala class may extend only one class, but it can extend many traits. A trait may contain in Scala anything that a class can. So in addition to abstract and concrete method definitions, it can contain initialization statements, properties. It could contain method bodies before the equivalent was allowed in Java itself. Traits can't have constructor parameters. That's sort of the main distinction between a trait and a class. So in 2.11, compilation of a trait gave rise, some trait T gave rise to an interface T. This included abstract accesses for any fields which were required by the trait but can't be implemented in the trait, obviously. It gave rise to a class, $T class, known as the trait implementation class. This contained the method bodies. That was the only place we could put them prior to Java 8. And they were static methods within the trait implementation class. The first actual class that inherited from the trait was required to implement the abstract interface methods in this trait by forwarding to those static methods in the implementation class. Furthermore, they had to provide any storage that was required, so fields and the concrete accesses so that the generic code up in the trait itself can access those properties of the trait. Oops. So just a quick view of how that looks. Here's a trait with a concrete method and a mutable property v, and that's compiled to this interface, the trait implementation class, and this, for every subclass that implements it, it does the additional work to provide the field and the accesses for the field, and provide the implementation of foo, which forwards to the corresponding method in the trait implementation class. So in Java 8, obviously we're allowed to put method bodies in interfaces, so we wanted to take advantage of this to clean up this sort of crufty encoding. The field encoding is unchanged because we don't have any new capabilities around that from the platform. But we said, well, let's leave the trait method bodies where it stands in the interface in the same way that Java default methods are encoded. The trait constructor can also stay in the interface as a static method. So that drops the need for the trait implementation class. And furthermore, it'll be nice if we can omit the need to write this little forwarder method in the every subclass of the trait. So in the happy case, that works pretty well. We just have a trait. I've left the properties out of the example this time because they're unchanged. You know, we emit an interface, we'll leave the method where it is, and the class does nothing. Unfortunately, that's not always going to work for us because Scala traits can extend Java classes. So in this example here, we have a trait T which extends C and overrides a method from C. Now this is a fiction that the JVM knows nothing about because the interface T obviously is only allowed to extend other interfaces on the VM. So if we just took this naive approach to our encoding, this d.foo is going to call the wrong method, right? Because virtual dispatch in the JVM is going to look up the superclass chain first before it constructs any defaults. It doesn't know that from Scala's linearization of the supertypes that the trait precedes the trait T precedes the class C, and thus the method in C the method in the trait T should be preferred according to Scala's rules. So what do we do? Well, we can just go back to our old trick of adding a forwarder to any such class. So class D here, we can detect that the JVM rules differ from Scala's rules. Okay, we'll have to add the class in. What we've chosen to do is only add this in the case where there's a disagreement. So it's sort of not the common case that traits are extending classes. And unfortunately, it's common enough that it's not something that we think we can sort of deprecate or remove from the language itself. You might see that this is also a new binary incompatibility. So where we've statically made this choice, you know, the world can change due to separate compilation. In general, the encoding of traits is very fragile from a binary compatibility point of view. Our changes here in Scala 2.12 help in a couple use cases, but the overall case means that changes to a trait typically requires recompilation of changes to subclasses that mix in that trait. So in this trait forwarder, we just saw we have to forward to a particular implementation of foo in a super interface. So how do we go about that? Well, we could use the same mechanism we're using in supercalls in classes to call a method and a parent and use invoke special. And that's sort of the path that we started down. First problem is that invoke special only allows you to call a particular named parent of the current class. Trait forwarders need the flexibility to call an arbitrary ancestor. This is sort of a Java language restriction, which you can argue is leaked into the JVM spec. But it's there, so we have to live with it. So what can we do? Well, sledgehammer approach here is why don't we just add redundant parents? Even though the user only extended T and T extended U, in the bytecode we can just say that their class extends T and U, and then or implements T and U, and that gives us access to any ancestor to target these supercalls. So yeah, the parent of my parent is my parent. My first attempt at this was just fairly quick. The big sledgehammer, I said, well, let's just name all transitive ancestors as parents of every class and see what happens. What could possibly go wrong? Startup time just ballooned. It was a bit of a surprise. I didn't see where it was happening. Eventually, I got a low enough level tool. Sorry, you won't be able to read that, but this is in the class file parser in the VM, filling in the vtables, looking at the same super interfaces over and over and over again as it's going up the chain. So it's clear that that idea was a non-starter. There's a variation on the theme though, where we do this conditionally just for cases where we actually need that ability to target something. Neither of those is a solution that we've settled on though, for reasons that we'll get into now. So in addition to these supercalls that the compiler has to synthesize to maintain Scala's view on linearization, the user is, just like in Java, allowed to write supercalls explicitly. Supercalls in classes in Scala follow the same language restrictions as those in Java. You can only call your direct, you can only call super, and meaning your direct parent class. However, you are allowed to call arbitrary trait parents. Because in the past in 2.11, these were just static methods. So our language could bind to any of them without restrictions from the JVM. So that's sort of, I think, the history of that permissiveness. Although it's some sort of an irregularity in the language between supercalls through classes and supercalls through parent or ancestor traits. Okay, so here's the basic idea. The user can, in trait U, call super.t of foo, and we'll compile that into a superfoo, meaning an invoke special. No, it's a bug in the compiler. That should be in the minus there. So what we found though is a little bit late in the game that invoke special actually doesn't do what we wanted to do. Even for invoke special that we're using in Scala 2.11, we discovered a bug where we do come into a mismatch between our view on dispatch and the VMs. So here's a quick example of that. Again, we've got a case where a trait is extending a class, which tends to be where we run into these corner cases. The trait T is extending A. Class C is extending B and T, and B also extends A. Now, in Scala's linearization rules mean that the order that you have your parents is significant. The last one wins. So here, we're trying to implement this call to super of T with invoke special. What we're trying to get a call to is method A, right? Because that's the super, that's the binding that we see of method M as seen from trait T. But what actually happens in the VM is we get B, because invoke special is actually doing a virtual dispatch. And too bad for us, we didn't look at that carefully enough back in the day. But so that's a latent bug that we've got in the compiler. So we've got this dilemma. Our supercalls are encoded wrong. Invoke special is not quite the right thing for it. What can we do? So we looked into using Indy, because we can do that now. We could call exactly the method that we want by reflecting on it in a bootstrap method using unreflect special. The problem is this requires elevated permissions. We're trying to emit this in a subclass, but we need the permissions of the class that we're naming as the target of this supercall. So without sort of set accessible and lookup.trusted, we can't do this. What we've settled on is the old approach of just adding static accessor methods. Unfortunately, we need to do this for every non-private method in a trait, because when we compile a trait, we don't know who's going to call super from below. Obviously, we don't have the power to add those retrospectively to third-party Java classes or third-party Java interface, third-party Java classes that are coming from either classes or interfaces. So the plan is to introduce a language restriction to tell people that they're not able to emit such a supercall. So despite that sort of hiccup and misstep along the way, we've still come to a pretty good solution, we think, or an improvement over the status quo. So in 2.11, people will look at their stack traces and see this sort of crufty t.class and call going through this forwarder method in the subclass itself. And now we just, the method body stays where it is, and stack traces are more natural and readable to people. The code is staying in the class where it was, so reflective tools that are looking for annotations and enclosing classes and these sorts of things are more likely to work well in this new world. And we got around this problem, as I said, with emitting static accessors. We may consider something more Indy-based in the future. That's sort of our plan, but there are other alternatives as well. Maybe we should put our current scheme behind Indy so we can change it kind of in a minor release. But we're a bit too close to the release to sort of take too many risks like that. So static access as it is. Okay, so we couldn't use Indy for that. What can we use it for? We're on Java 8 now, right? So first little side note is that we added support in the type checker for polymorphic signature. This is actually done in a minor release of Scala 2.11. So just by having an expected type of int here, we get the right method descriptor for this polymorphic invocation of method handle.invoke. We've got a to-do item to add the same thing for the newly spec'd polymorphic signature stuff in var handles for Java 9. Scala has symbol literals, and quote foo is a shorthand for a call to scala.symbol with the string foo. These are interned in this apply method of scala.symbol. And in addition to interning, any class that has these symbol literals in them will cache them currently in a static in that class. So if they're defined within a loop, the literals only looked up the once, and then every other iteration through that loop is picked up from the static in the field. Now, private statics are not supported in interfaces in Java 8, so we sort of had a choice here. Should we just publicize that static field that we're using as a cache, or can we indify it? And this is sort of a perfect application for one of these link time constants that John was referring to, and the implementation is as you would expect. It's very straightforward to use Indy for that use case. That's sort of the first little toe in the water that we have with invoke dynamic. Scala also has structural calls. So this declares that C is some value of any type which has a close method, a void close method. And this is compiled into reflective calls with, again, a static cache in the host class to keep recently used reflection artifacts around so that lookup's not done time and time again. Again, for the same reason, we don't have private static fields at our disposal in interfaces where we're trying to leave trait bodies now. So we use exactly the same trick, and we just put the cache behind a constant call site in an invoke dynamic bootstrap. We did actually prototype using Dynalink, which I think is the next talk today, to outsource the job of maintaining this cache of reflection artifacts. It's a pretty good fit. However, our structural call part of the compiler has some special cases for dealing with some fictional methods that our compiler sees. We have a plus method on string, for example. So future work here is to augment Dynalink to understand these handful of fictional methods and then outsource that job and actually get away, reduce the special support in the compiler just down to emitting a single indie call. So we've had a couple use cases here where we're emitting invoke dynamic. We sort of got sick of special casing each of these use cases in our compiler backend, so we created an AST encoding for arbitrary indie calls. Scala has a compile time macro system as well, which can expand any application into arbitrary AST. So you put those two things together and you have like an undocumented, experimental, full of caveats means to actually have library level support for indie. So we played around with a few examples of this and we'll just show you what's possible. So just a quick cheat sheet about Scala macros. It's an experimental feature introduced in Scala 2.10. It's experimental in 2.11. It's experimental in 2.12. It's stable enough and used relatively widely, but it's experimental because to make a macro API for a typed rich language like Scala, there's a huge surface area to let people manipulate and interact with your trees and symbols and types. And there's still research into finding a more minimal way to expose that API. So client code of a macro looks, feels, type checks like a regular method call. Arguments in particular are type checked before the macro is expanded. There's no way that you can sort of subvert typical type checking order by having access to untyped arguments. The macro author writes a pair of methods, a macro declaration, which is the type signature, and implementation method, which is the AST transform. The standard lib, we have a couple macros. We have string formatting that sort of statically checks that you've got the right number of the right format specifiers and those sorts of things. We've also got, to support macro authors, a special macro for quasi-quoting that lets you embed snippets of Scala code, and that expands into the code which would produce the trees for that particular syntactic structure. And the quasi-quote macro is also possible to use for pattern matching on trees as well. That's one of our kind of ideas on how to make a smaller API for people to use. If they're just dealing with quasi-quotes, we don't necessarily have to support the whole tree API directly. So that's all you need to know about Scala macros. So let's have a look at an example of this. Let's say we'd like this kind of code to work. We want to compile some regex and then make some calls on it. But next time we come through here, we don't really want to pay the cost to recompile this regex because it's just based on a literal string. And furthermore, if we have some invalid regex syntax, let's tell the user about that at compile time. So how can we implement that? We can write a macro. So down the bottom, we have the macro declaration. So to the user, that just looks like a regular type signature. And that's telling the compiler that this is the method that it should call reflectively during type checking. Here's the guts of the macro. It has one argument tree, which it can pattern match on, determine that it's a literal string. We can compile the pattern at compile time. check that it's valid, report an error, position that right at the right spot in the string for them, and emit our encoding of Indy passing through the constant bootstrap argument. In this particular case, if they didn't pass a constant here, we can just leave everything until runtime and compile the non-constant argument. And this is an example of using the quasi-quote macro to create a tree within a macro implementation. The bootstrap method here couldn't be simpler. It's just a simple compile time constant calling pattern.compile. And yeah, so that's a kind of a neat way to implement these compile time constants. You know, John wrote this long post to the mailing list about a week ago that has a bunch of great ideas on how that might come into Java. Or yeah, my idea is just to encourage anyone who wants to prototype with that stuff. You know, aside from the bytecode weaving approach, Scala's macro system might also offer a good vehicle for exploration. You know, and then just thinking of other use cases where this can be of some benefit to the community. You know, perhaps we can make a Scala macro library that lets people abstract over the differences between Java 8 and 9. So they call, for example, you know, compare and set. And this at link time will say, what platform are we on? Okay, we're on 8, let's use unsafe. Okay, we're on 9, let's use a var handle. Because, you know, the cadence of Scala releases mean that it might be a while before we can target and require 9. So this maybe gives us a way to let people take advantage of 9 before that point. So just to take the idea a tiny bit further, you can imagine if you write too many of these macros, they start to get very boilerplatey. You're really just checking that you've got some constant, some of your arguments are constants, and then forwarding those as bootstrap methods down forwarding those as arguments to some bootstrap method. And your bootstrap method is just running some little snippet of code. So what if your bootstrap method was an interpreter, and you can pass it the program to interpret from a generic macro? So, you know, let's say that we've got some partially evaluate macro, which knows that, you know, construction of immutable lists here with constant arguments is something that we can lift out and do at link time. You can conceivably imagine that this macro can generically take its argument here and convert that into an invoke dynamic call. And the open question is how you encode this program. You know, the new constants that kind of were on this ideas list for of John's might give you a structured way to do it. I'm sure there's plenty of unstructured ways to do it as well that would probably work today. There's actually a lot of research being done in our neck of the woods into the ideas of staging. So, you know, if you're interested in seeing how staging has been thought about in the Scala world, here's a couple papers. I think this integration with link time evaluation gives a new flavor to it, so it'll be interesting to see if there's some further research goes on into that. Okay, final topic is just a quick talk about lambdas. You know, in high level, there's not too much to talk about here because you're all familiar with how lambdas were encoded in Java 7, you know, anonymous inner classes of function types that sort of existed by default in libraries, or, you know, runnable and so on in the standard library. And in 8, the same types are used, but with invoke dynamic to defer spinning up those classes. So what we've done is the same at a high level, but we had a couple implementation challenges along the way, so I thought I'd just share those with you. So our first design principle was to say, let's use lambda metafactory. You know, just for starters, it's satisfied our laziness. We didn't have to write our own metafactory. And second, it gave us the best chance, we thought, of sort of like buying into any future performance improvements in Hotspot, which perhaps intrinsify something by knowing the behavior of this particular bootstrap. But what was Lambda Meta Factory unable to do for us? Well, the first sort of minor annoyance is that there's no way to customize the toString for the generated class. So this represents a regression in Scala functions. You know, we used to override toString to say function, and now we get lambda 1, 2, 3, 4, 5, 6. Second, Lambda Meta Factory is able to do type adaptation if the signature of the method of the functional interface method differs in small ways from the Lambda implementation method. It will insert boxes and unboxes and casts as needed. It turns out that these were not sufficient for our purposes. So in Scala, unboxing of a null is a 0. In Java, it's a null pointer exception. That sort of stems back to Scala's integration of the primitive types into the unified type system, where we have object, any, and any val, and the primitives under here. So
there is a standard combinator that does that, but you can't get to it inside.
Yeah, once we hand over to Lambda Meta Factory, we have no further say in the output. In addition to primitives, Scala has value classes. Value classes are wrapper types like, let's say, meter, where the compiler will erase meter to its wrapped type. And functions that involve value classes as either their arguments or return types also generate code which Lambda Meta Factory has no idea how to box and unbox. So the solution to this wasn't too hard. We just had to say, if our Lambda implementation method will be adaptable by Lambda Meta Factory, fine, hand it over directly. Otherwise, our compiler will just generate an adapter ahead of time and use that as instead. Again, we do that selectively to try to keep call stacks a bit smaller. With Lambda heavy code, they're kind of high enough as it is. Yeah, and another special case here is that void return types in Scala can be unified with functions from a generic function type, and that's not possible in Java today. Yeah, so these are just examples of the behaviors of Scala functions and boxing and unboxing of void and primitives, which we've had to maintain by generating these little adapters. Yeah, so we live with a new toString. We're just going to tell our users that that's how life is. They wanted a different one anyway. They want to show the code to see where it is or the line number, and you can't please everyone. So that's where we'll sit. We'll selectively use these new adapter methods as the Lambda target. A further small challenge was with Scala's specialized functions. So Scala's got specialization, which is sort of, trying to solve the same problems as anyfied generics in Valhalla. It's all done ahead of time in Scala, which has the obvious problems of, too many combinations of specialized variants and so on. But we do have specialized function types. So a function type from int to int doesn't incur boxing if the caller to that is non-generic code. Specialization is implemented by having a bunch of specialized sub-interfaces of the generic interface. Just sort of due to an implementation quirk of the specialization phase of our compiler, the wrong method is left abstract for it to be directly used as a functional interface. So we just had to write a bunch of Java code to make adapter functional interfaces for these ones to re-abstract the primitive to primitive methods. That's not something that's any fault of anyone but our own. Last challenge here is serialization. I was chatting to Brian about this, and he shared all the same pain. So Java-C treats serializable functional interfaces as the exception rather than the norm, and only generates the serialization code both in the serialization code in the Lambda itself and the corresponding deserialization code in the host class selectively if the functional interface extends serializable. Scala lambdas are, that implement function n are serializable always, so we have sort of a different starting point there for our design process. In Java, there's a bug open that says if you have too many serializable lambdas in your class, you'll just get a method size too big exception because when you're generating code, because the deserialized lambda has specific code for each and every lambda in the current class. So we didn't want to sort of run into that problem. So what we'd use instead is a generic lambda deserializer. So the body of lambda deserializer conceptually just forwards to generic code, which calls lambda metafactory in user space. And this is then backed by a cache specific to that call site, so we're not doing the same work over and over again. That cache is kind of hidden away behind the invoke dynamic call site in Java C's version of this. To host that cache, we use Indy again, to actually have a static field, but hidden away behind a particular call site. Now, there is a trade-off. The behavior of Scala and Java serialization, deserialization actually of lambdas is slightly different. Java is a little bit more restrictive on deserializing something where the types of the parameters have changed or some signature changes have happened. Scala isn't able to fail fast because of the fact that this generic lambda serializer doesn't know really the current state of the lambda implementation method in the lambda host class. But it's no worse than it was in Scala 2.11, where we didn't make strong guarantees about serialization and deserialization with different versions of code. We've had a couple other little issues. Scala has a feature called lazy vals, which sort of encapsulate sort of double-checked locking pattern as a language construct, synchronizing on the enclosing class. Suddenly now, with lambdas being hosted in an implementation method in the host class of the lambda, rather than in an anonymous class that's spun up, we've got a different lock scope. That's a tough one. The only real solution we have here is to have a mode of the compiler which just doesn't use lambda metafactory in case someone hits a deadlock and they're trying to diagnose it. But there's nothing particularly sane we can do here other than just educate and document and give people some tools. Locking's hard. Hidden locking is arguably a very bad idea, but it's baked into the language and it's convenient, but there's a price to that convenience. For the same reason that method body, the body of the lambda is now in the host class, there are subtle differences to the amount of code that was being captured when you instantiate the lambda. Do you need a reference to the outer class to call a non-static method in there? So in earlier versions of our lambda encoding, we did have this problem where suddenly the lambda would become too big because it's holding on to more than it needs, or equivalently it would become not serializable because it was holding on to an enclosing class which is not serializable. Fortunately, this was largely solvable. We already had some analysis that tries to make lambda implementation methods static. We just had to extend this to transitively say if there's a chain of things which don't refer to anything except other lambda implementation methods, we can make a chain of them static. So long story short, we've managed to sort of restore our old benchmark of what things are serializable and how big they are, as far as we know so far. We're going into release candidate phase very soon, and we may have some more surprises, but that's what it's for. So what's next? 2.12 RC1 is coming out about the end of the month. After that point, we're going to start working on Java 9 support. We're collecting requirements at the moment. There's going to be a little bit of work there, both for Jigsaw, for some subtle changes in the VM that Dimitri's just found out about. We're also going to be investing in benchmarking performance of the compiler and library. You know, we want to try to cherry pick as much of the insights that Dimitri is finding in his research, and see if we can find any ways possible to deliver those to people who are using the current version of the Scala compiler. So with that, I'll wrap up.